There is a subtle thrill that runs through anyone who looks at the sky, knowing that not everything crossing it belongs to our cosmic lineage. Among airplane trails and the orderly orbits of planets, today a body travels that does not speak the dialect of the solar system. It is a comet born elsewhere, in a protoplanetary disk around a star that is not our own. It has spent eons in interstellar darkness, preserving within its frozen veins the chemical tale of the place where it grew up. Now, as it bows to the sun's gravitational field, it allows itself to be studied as an uncontaminated sample from a distant laboratory. The idea of witnessing this encounter is not only poetic, it is a unique natural experiment, because such an object offers us in one sweep the paleoclimates of another system, grain dynamics, isotopes, rotation, activity, all under conditions we cannot reproduce at will. For us, the story takes shape on July 1, 2025, when a telescope dedicated to sky surveillance detects a faint signal in the direction of Sagittarius. That glimmer bears the hallmark of difficult things: low magnitude, crowded stellar background, the risk of mistaking it for noise. Yet just a few days of follow-up are enough, and the orbital track reveals its nature. It is not a closed ellipse around the Sun, but a hyperbola. The language of orbits is clear. Whoever arrives on a hyperbola enters, curves, and leaves. It is the third traveler of this kind we have intercepted after Oumuamua and Borisov, and the scientific excitement is immediate. Ground and space observatories activated, archives scoured for pre-discovery images, bursts of astrometry to pin down orbital parameters with ever smaller uncertainty. The dynamics already tell much about the protagonist. Far from the Sun, this guest glides at speeds that, on a human scale, sound like fantasy, over 200,000 kilometers per hour before entering our domain, with acceleration increasing as it descends the gravitational hill toward perihelion. That very passage, its moment of closest approach to the Sun, falls at the end of October 2025, in the hours when our star can truly stir the volatiles nested in the pores of the nucleus. These are the days when spectrographs hunt for chemistry, the fingerprint of carbon dioxide, the discrete voice of water, the atomic lines of refractory elements revealing fractures and sublimations of tiny metallic inclusions. Meanwhile, there's a spectacular waypoint, its closest approach to Mars in the first days of October 2025. Observing an interstellar comet from Martian orbit adds a precious geometry, different angles, different perspectives, different parabolas of grains pushed by solar radiation and particle winds. The sequences collected by orbiters are not mere cosmic clips. They allow us to better separate the components of the coma, to measure how closely the tail aligns with the anti-sun direction or how much it twists due to anisotropic jets, to estimate the orientation of the rotation axis by comparing brightness variations with the rhythm of plumes. Of the solid object, the nucleus, we see only its effect. The surrounding coma is a shining haze that hides the core like a curtain. Yet, by combining high-resolution images and light-scattering models, we can place limits on its size. A diameter of a few kilometers at most, perhaps less than one in the most extreme case. This is not mere numerology. Size determines how heat penetrates, how fast thermal cracks open, and what kind of jets emerge when new conduits form toward the surface. A small nucleus responds almost nervously to the Sun, a larger one filters and delays. Variations in the light curve, micro-outbursts, and the amplitude of tail asymmetries become indirect clues to the internal structure, porosity, ice layering, possible sintered crusts. On the compositional front, the picture becomes intriguing. In domestic comets, water is almost always the main driver of activity at moderate distances. Here, instead, several observations suggest that carbon dioxide plays a larger than expected role, with ratios prompting a reconsideration of the nucleus's formative environment. An excess of carbon dioxide compared to water could mark a formation region at lower temperatures, or a different irradiation history while grains grew in the disk. Carbon dioxide condenses and remains trapped in porous matrices in a temperature-sensitive way, and its anomalous abundance hints at a construction site with thermal gradients unlike those near our young sun. To spice things further, metallic behavior adds another flavor. Nickel lines appear stronger than expected relative to iron, as if metallic inclusions follow different release paths. Possible explanations? Micro-impacts between grains in the coma-liberating atomic species, differences in refractory grain sizes, or an initial chemistry where metallic phases existed in different physical states. Nanoparticles, compounds, alloys, with distinct sublimation and sputtering thresholds. A word must also be spent on early water, signals of hydrogen oxide activity at distances where, normally, our comets show only faint breathing. This scenario carries the hypothesis of micropore networks and fractures connecting subsurface reservoirs to the nucleus's skin, allowing heat to free molecules before sunlight becomes extreme. Or perhaps these are freshly exposed regions from thermal landslides that have uncovered new material. In any case, the idea of a more efficient than average internal hydraulics suggests a different thermal past, maybe weak but repeated heating cycles during long sojourns near other stars, capable of stitching the microstructure without fully vitrifying it. One aspect that always captures public attention is the artificial hypothesis. It's a powerful narrative temptation, accelerating objects, unusual chemistries, strange orbits. Here, however, the data bring fantasy back to Earth. Cometary activity is evident, the response to solar distance is consistent, and the trajectory is that of a natural visitor. If there are anomalies, they are precious precisely because they are natural, differences in volatile ratios, in released metals, in the early onset of water, in grain texture. These statistical deviations help us grow. We learn that planetary systems do not all cook the same recipe for icy rocks. The universe, instead of staging miracles, speaks to us in different accents of the same physical language. And then comes the question of age. The typical velocities and dispersions of interstellar populations suggest that such objects could be older than the solar system itself. If 3I ATLAS truly dates back from a few to over 10 billion years, then what we are measuring is the stratigraphy of a fossil remnant, one that survived dynamic ejections from the dawn of its native system and was later stirred by stellar traffic. A mobile fossil. It may have seen the Milky Way in epochs the Earth never knew, crossed gas streams, shock waves from stellar explosions, and arms of varying density. Every grain evaporating in its coma carries a tiny trace of that past. And it is precisely on this idea, traces as clues, that the next step should focus, because these intruders are not mere spectacles, they are instruments. If we can design the right encounter, the leap in knowledge would be immense, for a close rendezvous would give us what we now infer only indirectly. An image of the nucleus would resolve its shape, elongated or compact, the presence of ridges and cavities, the ratio between dark surfaces and brighter patches. A lidar or stereo camera could measure slopes, fractures, debris. A mass spectrometer could sniff the coma, separating isotopes of hydrogen and oxygen in water, carbon variants among carbon dioxide, Colorado, and organics. A dust analyzer could reveal the grain size down to submicron fractions. The obstacle, however, is purely ballistic and organizational. These objects arrive without sufficient warning, accelerate and flee, while our engineering needs years to prepare a spacecraft. Hence the philosophy of ambush missions. A probe parked at a gravitational equilibrium point, ready to launch as soon as a new visitor's parameters are known. It's an elegant response to a natural constraint. If the train won't slow down, you wait on the platform with your backpack already fastened. Meanwhile, Earth and Mars become two synchronized stands from which to squeeze out data. Observing 3I ATLAS from different geometries means, for instance, decoding the structure of its jets more precisely. If the coma shows a dust fan broader than expected along the antisolar direction, there may be a non-trivial contribution from large particles retaining inertia, or a tilted rotation axis causing diurnal modulation of activity. If the tail shows a slight curvature, we may be witnessing a mix of radiation and solar wind interaction, ionizing part of the gases and dragging them into a magnetic channel, allowing us to distinguish the dust component, yellow tail, from the plasma one, blue tail, and estimate molecular production rates. The angular difference between the two tails and their thickness become rulers for measuring the nucleus's breadth. On the thermal plane, the comet's day-night cycle is a fascinating laboratory. Rotation exposes fresh regions and pushes warm ones into shadow. In every turn, expansions and contractions stress the crust, cracks open and close, pores heat up and release gas, then cool down and re-freeze the heavier volatiles. If the rotation period is short enough, the surface never reaches equilibrium. If long, steeper gradients may arise, favoring surface landslides and sudden vents. A dense photometric campaign, crossed with time-resolved spectroscopy, can reveal these rhythms, a symphony of peaks and calm that, properly read, tells where the rotation pole lies, how oblique it is, whether the nucleus precesses, whether persistent jets slowly alter its orientation by reaction. The chemistry remains the most captivating chapter. A high carbon dioxide-hydrogen oxide ratio opens scenarios of origins far from our solar system's average. If the comet formed beyond its own system's water snowline, in an environment that favored efficient trapping of carbon dioxide, then its birth disk had gradients and pressures capable of preserving that molecule without diluting it into hydrates or delaying its release. An alternative hypothesis invokes its later history. Passages near hot stars that cooked surface water while leaving carbon dioxide intact deeper down, or shock waves and cosmic ray doses sufficient to transform part of the water ice into other species through radiolytic processes, with consequent compositional remixing. Isotopes would be the supreme judges of this mystery. D-H ratios in water, cubed C, squared C in carbon, to the power of 8O, to the power of 6O in oxygen. Measurements of this kind would allow us to compare 3I, ATLAS's signature with solar system comet families. If it resembles none, we'd have further proof of the galactic workshop's diversity. If it matches one, we might infer unexpected evolutionary convergences. Metals, as often happens, are the silent actors that change the plot. Nickel and iron, for instance, have different binding energies and release behaviors. Subtle differences in particle size, in alloy content or mineral phases, sulfides, oxides, pure metals, can alter the observed spectral line intensities. If 3I, Atlas's coma shows nickel overrepresented, one might hypothesize that metal sulfide grains fragment more easily under certain conditions, or that the porous microstructure favors localized heating of nickel-bearing inclusions. Here laboratory and modeling chase each other. Vacuum chamber experiments with real grains heated by lamps simulating the solar spectrum can confirm or refute hypotheses. Microphysical simulations of thermal conduction between icy matrix and solid inclusions help predict where and when releases occur. Even long-term dynamics tell a collective story. Interstellar objects like this are not born free, they are expelled. At first they are planetesimals in relatively calm orbits around their star. Then system evolution. Migrations of giant planets, multi-body instabilities, resonances, flings them beyond escape velocity. Some remain trapped in local Oort clouds. Others are launched into the space between stars. Their current velocity is the outcome of those gravitational kicks and subsequent wanderings around the galactic center. Seeing one pass here, now, means taking part in a cosmic statistic. How many ejection systems typically produce? What size ranges are most probable? What fraction of expelled planetesimals carry complex organics? And what role these foreign bricks play in the chemical seeding of the systems they cross? The theme of direct exploration, of course, remains the dream. In the past, people have discussed the possibility of repurposing spacecraft already in orbit around planets or parked for other missions. redirecting them with bold maneuvers to chase the intruder during its near pass. But between propellant limits, pointing constraints, ongoing mission priorities, and above all the speed with which the window closes, feasibility dwindles. The operational lesson is crystal clear. We need modular, lightweight, ever-ready platforms with essential but versatile instrument suites, mass spectrometer, high dynamic camera, dust analyzer, magnetometer, and flight profiles already tested in simulations for a range of possible orbits. The stakes are high. The first probe to embrace an interstellar object up close will deliver a revolution of data comparable to what Rosetta gave us for solar system comets. Meanwhile, the patient work of mapping continues. Every photometric measurement helps fix the dust phase law. Every spectrum adds a tile to relative abundances. Every deep image of the tail sketches the chronology of emissions in the preceding weeks. By cross-referencing all this with thermal and dynamical models, a plausible biography can be reconstructed. How often 3I, ATLAS has suffered comparable thermal stresses, how frequently it lost surface layers, how many active regions dominate mass flow, whether there are crustal plates thick enough to locally suppress activity for long periods. It is a nameless biography of its parent star, but not a mute one. It speaks through numbers, the most honest language we know. There is no need to force the exceptional to grasp the wonder. An icy rock carrying the chemical climate of another stellar cradle and, by pure geometry, crossing our orbit is already a story rich enough to fill an entire season of discoveries. Today we see its coma grow and its tail stretch beyond 100,000 kilometers. Tomorrow, and in astronomy, tomorrow may mean just a few weeks. We'll watch it recede, its activity fading, its spectral signature changing with decreasing sunlight. And then it will vanish from view, return to the darkness it came from, fleeing into a region of space no telescope can follow. But it will not have left emptiness behind. It will have left a trail of data, a new grammar for reading what may come next year, in 10 or 100. Each time such a visitor crosses our sky, the galaxy reminds us that we are not an isolated case but one sample among many. The physics is shared, the recipes diverse. And our curiosity, as long as we have eyes and instruments turned outward, will keep reaching toward the next messenger. If you've read this far, it means you love curiosity as much as we do. If you enjoyed this journey, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.